evening,
Yes, sir.
everyone. We are in the week 3 problem solving session of the NPTEL course Control Engineering. And week 3 is about block diagram reduction and time domain characteristics. I am Teja Golla, a fifth year research scholar working under Dr. Santanu Kapat at Embedded Power Management Lab, IIT Kharagpur. Let me share my screen. Yeah, Neeladri, good evening. So I hope all of you have gone through Sir's lecture this week. So this week is also a very interesting topic. So basically it consists of two things. One is the block diagram reduction and second one is the time domain characteristics, and it also includes the steady state error, one subtopic of the time domain characteristics. So first I'll start with the block diagram reduction. So Sir has discussed about Mason's gain formula. But in order to apply Mason's gain formula, we need to know what is signal flow graph. So for a given block diagram, we'll have to draw the signal flow graph, and from the signal flow graph then we can apply Mason's gain formula so that we can reduce the block diagram. So what is a block diagram reduction? See, in a given system we might have many gains, feed forward terms, feedback terms, many summer blocks. So it can be a complicated system. From input to output there may be n number of blocks, but we need to know the input to output transfer function. So the block diagrams that are there in between input and output, if we are planning to reduce into a single gain, just an input to output transfer function, that is called block diagram reduction. So we can use some techniques to directly reduce the block diagram, but if the complexity increases, there has to be a methodological way so that we can follow that to reduce the given overall block diagram to a single input to output transfer function block. So in order to do that, Mason has come up with a gain formula which we can use to reduce the block diagram. But before that, we need to draw the signal flow graph. Only to the signal flow graph we can apply Mason's gain formula. So let us start with the signal flow graph. So I hope my screen is visible for everyone.
Yes, sir.
Okay. So in signal flow graph, first we need to understand two things. One is the node. First thing is node, and second one is branch. Okay. So let us consider the famous unity feedback circuit that we have discussed last week. So I'll consider one very simple circuit. So we have a summer, and then we have a feed G, and then we have output Y of S, and then we have feedback gain, say H, and then input R of S. So now if we take plus and minus, and then say now I want to do the block diagram reduction. Okay, we are planning to do the block diagram reduction. So can anyone tell me what will be the input to output transfer function? If we simplify,
G divided by 1 plus GH.
G divided by 1 plus GH. Very good. So uh, just a minute. I think there is some issue with my writing pad. I'll disconnect and connect. Yeah, now it is fine. Can you see my screen?
Yes, sir.
Yeah, okay. So we have our block diagram, which is whatever you have mentioned, G by 1 plus GH. Okay. So this is our output Y of S and input R of S. Okay. So now this is called block diagram reduction. Okay. So how we are reducing it? One way is we have solved for the input to output transfer function using this block diagram itself, and we got that. But now, is there any other way? First, we'll learn how to draw the signal flow graph. So in the case of signal flow graph, if you see all these lines are there, right? So this signal will become node. So node is what? The signal that is there that will become node. So if I call this, we know that this is error of S, E of S. So all the signals that are there will become something called node. Node is just a point. So R of S is 1 point. Maybe I'll use a different color so that we can make out what is a node. So we have R of S 1 point, then we have E of S 1 point, then we have Y of S another point. Okay. So now from RFS to EFS, so there is no gain, right? So there is only a summer block. So there is only gain 1 because EFS is R of S minus something, right? So there is only gain 1. Okay. So let me mark this also. So these nodes are, these are R of S, E of S, and then Y of S. So the signals that will become nodes. Nodes are these points which are having the signal information. So from R of S to E of S, there is a forward gain of 1. So this is the branch. So branch is the path that is connecting the nodes along with the direction of the signal with gain information. So now E of S has R of S information with a gain of 1. And what does Y of S has? Y of S is G into E of S, right? So Y of S is gain G into E of S. But E of S also has a feedback. E of S has a feedback of minus H from Y of S. So from Y of S, there is a negative feedback of minus H. So now if I see this signal flow graph, R of S is only input. So this is my input and this is my output. So basically I should have one more connection. I can make it like this. Say this is the Y of S and gain 1 to the output. So this is my Y of S. So now if you see, this is my input side and this is my output side. And the gain is of course 1. So if you see, E of S is what? R of S into 1 minus H of S into Y of S. So E of S is R of S minus H of S into Y of S. And from here, Y of S is E of S into G, which is also the same. So basically, we are representing the given block diagram into something called nodes and branches with gains, so that this entire block diagram is now represented in a easier diagram. So these dots are called nodes, which represent these signal points. These dots, you see these dots, these are, I'll use a different color. So these are node. And the connection between these nodes with the gain information, they are called branches. So this is how a given block diagram can be redrawn into signal flow graph with nodes as well as branches. So is this clear until this point?
Yes, sir.
Okay. So if you have any doubt, you can ask. So now using this signal flow graph, now we'll learn about this Mason's gain formula. So Mason's gain formula also will be needing a certain nomenclature that we'll discuss. Then we'll go to Mason's gain formula. So the nomenclature is important. Note how it is coming. The signal will become the node, which is the dot point. Representation is dot. And then the gains or the path that will become branch. Direction, it consists of the direction from which signal to which signal it is going. Also it consists of the gain. Because this is a negative feedback, I have incorporated the gain in minus h itself, because here there are no summers. So the gain it itself will have the positive and negative information. Is that clear?
Yes, sir.
Okay. So now coming to Mason's gain formula. For that, there is some nomenclature that we need to know. Nomenclature. And we'll also solve one problem to understand. Once we solve the problem, then we'll move to further problems where we'll apply it and we'll learn the concept better. So first one is the input node. So in this case, in the above example, what is the input node? Input node is R of S. So input node only has outgoing branches. So there are no incoming branches. Outgoing means from it, that point, the signal is going outside. So input node It has only outgoing branches. And similarly, output node, there is something called output node, which has only incoming branches. Like y of s. In the above example, only incoming branch is there, no outgoing. So that is the output node or output side, input side. So basically, I should stick to the nomenclature and should have called it node. So let us use the node. So this is the input node and this is the output node. So that the nomenclature will be clear and there will not be any confusion. So these are the two nodes, input node and output node. So the signal flow graph will have one input node as well as one output node. So now in this example, RFS is the input node and YFS is the output node. So now coming to the next one, path. Path can be we are traveling from one node to another node, but no node is covered twice. So here I can call R of S to E of S is one path, R of S to Y of S is one path, but we should not go in loop so that no node is traversed more than once. So path is we are considering the path from one node to another node, but we need to consider that no node is traversed twice. So here R of S, E of S, and say this is some, say this is, we'll name it as Y dash of S. So I cannot say R of S, E of S, Y dash of S, and come back E of S, Y dash of S, and Y of S. So no node should be traversed more than once. So only each node will be traversed once. So no node is traversed more than once. So we have to cover each node only once. Now, under this path, there is something called forward path. So forward path is it traverses from input to output. Input to output. So it traverses from input to output and no node is covered more than once. So there can be more than one forward path. We'll see an example where there are more forward paths. And in that case, how to get the Mason's, apply the Mason's gain formula, we'll look into that. Now coming to loop. Loop, you understand from the word itself. So it originates and ends at the same node. So in this case, this is the loop. E of s, y dash of is one loop because it starts from that node and ends from that node. So that initial node will be the end point as well as the originating point. So originates, the path will originate at and at the same node. Path will originate and end at the same node. At the same node. Now the last nomenclature, non-touching loops. Non-touching loops means there are two loops and they are not touching each other. Not touching each other means there is no common node. Non-touching loops. So two loops without any common node. Two loops without any common node. In the above example, it is simple and straightforward. So we don't have more than one loop. So it is difficult to understand what is what. So we'll take an example. But before that, let us write the Mason's gain formula. I hope everyone is following. If you have any doubt, please stop me at any time. Mason's gain formula. So the overall gain or the transfer function. So the overall gain is something called sigma k equals to 1 to n pk delta k by delta. So this is the formula. Let us see which is what, which term corresponds to what. So here n is the number of forward paths. Let us define that first. So n is number of forward paths. and pk is the path gain. Pk is the path gain of the kth forward path. Path gain of the kth forward path. And then delta is called determinant, and delta is very crucial. Let us see what is delta. Delta is called determinant of the given circuit or block diagram. Determinant, sorry, my bad. Determinant. And delta is defined something like this. So delta is equals to 1 minus sum of all individual loop gains plus sum of product of all combinations of non-touching loops loop gains, again minus sum of product of all combination of this is actually two non-touching loops, so I should mention of two non-touching loops of two non-touching loops. Again we'll have minus sum of product of all three non-touching loops and up to so on and up to so on. And delta k is delta of that part of the graph not touching the kth forward loop. So delta of the graph that is not touching the kth forward loop. Not touching the kth forward loop means we have to consider all the loops that is not touching the kth forward loop. So the context or the nomenclature may be slightly confusing or not clear, but once we solve one problem, it will be more clear. So until this point, if you have any doubts, you can ask, but if you are not sure how to apply this formula, then just hold on a minute, we'll solve one problem, then it will be clear. Any doubts until this point?
No, sir. No.
Okay, so let us solve one problem. Then if you have any doubts, then I think it makes more sense. So let us quickly solve problem. So I'll take the problem that sir has considered in his lecture for this. So let me quickly draw. And then nodes, we have U of S, then A, then B, then C, then D, then E, and then Y. So we have U, input U, A, B, C, D, E, and then Y. So the gains I'm using black color. So there is a gain of 1, and then there is a gain of G1, and then there is a gain of G2, and then there is a gain of G3, G4, and 1. G3, G4, and then 1. And then there is H1, minus H1, and then there is minus H2, D2C, and then E2D, minus H, and then A2E, G5. Okay. So this is the circuit. So for any circuit, first we have to draw the signal flow graph. This is the signal flow graph. We have discussed at the beginning how to draw the signal flow graph for a given block diagram. Now, once the signal flow graph is done, we have to directly apply this formula. But for applying this, first we need to know number of forward paths. So forward paths are needed, path gain of each forward path, and then we have to calculate delta, and then we have to calculate delta k, and then plug in. So let us start with the forward path. Forward path is starting from the input node, we have to go to the output node. So input to output node, and each node should not be traversed more than once. So for this given problem, can anyone tell me how many forward paths are there? First, let me write the forward paths. So we have to
Two are
start
there.
from input, and then end at output. Anyone?
Two forward paths.
Okay, what are those? You tell the node points.
U, A, B, C, D, E, Y.
Yes.
U, A, E, Y.
UAEY. Very good. UAEY. So these are the two forward paths. So our N is 2 basically. So N is 2 because there are two forward paths. And then we know the path gain, right? Can you tell the path gain of this one and path gain of this two?
1 into G1, G2, G3, G4.
Very good. So this is G1, G2, G3, G4. And then the other one?
G1, G4. Sorry, G5.
G5. Only G5, right? 1 into
Only
G5.
G5.
Yes.
Yes.
So forward paths are done. So I know my K is equals to 1, starting from K equal to 1, N equals to 2. Now I have to calculate PK, which also I have done path gain of each path. Now before going to delta K, we have to let us see delta. For delta, we have to find the loop gains of the individual loops. So let us start with the loops. So how many loops are there here? Loop means we have to start and then come back to the same point, traversing in the same direction that these branches have. So how many loops are there?
3 loops, sir. 3.
3 loops. So let me name them L1, L2, L3. So L1, L2, L3. So what are the gains of these loops? Because in our delta, it is sum of all individual loop gains. So we are dealing with the loop gains only. So whenever we have loop, we have to see individual loop gains. So what are the loop gains of each? 3 loops are there, right? This is one loop, this is another loop, this is another loop. So what are the loop gains of these 3?
One is minus H1, sir.
Very good. Other one?
Minus G3H2.
Yes, very good. Other one?
Minus G4H3.
Minus G4H3. Very good. So everyone agree, right? There are 3 loops and the loop gains is minus H1, minus G3H2, minus G4H3. So if till now it is clear, can you tell me what are the non-touching loops here? Means 2 loops you should consider and there should not be any common node.
L1 and L3, sir.
L1 and L3, right? Very good. So I hope others are following.
L1 and L2 also, and L1 and L3 also.
Yes, L1 and L2, L1 and L3. Very good. L1 and L2 also. So now if I have to calculate the product, so now two non-touching loops, sum of the product of all combinations of two non-touching loops minus sum of product of all combinations of three non-touching loops. But three, there is some, here they are touching. So three non-touching loops are not existing. So from here, it is ignored, means it is 0. So L1 and L3, what is the gain? G4, H3, H1, right? So the gain is G4, H3, H1. L1 and L2, it is G3, H1, H2. Everyone agree? Till this point, is this clear for everyone, the nomenclature and everything?
Yes, sir.
Okay. So now let us calculate delta. Delta is constant, right? It is in the denominator. So let us calculate delta. Delta is equals to 1 minus summation of all individual loop gains, which is minus H1 minus G3H2 minus G4H3 plus summation of product of all possible two non-touching loops, which we have already done. So we have G4H3 H1 plus G3 H1 H2. After that, we don't have anything. Three non-touching loop doesn't exist in this problem. So after that, there is no term. Now, let me calculate delta, simplify it. So delta is 1 plus H1 plus G3H2 plus G4H3 plus G4H3 H1 plus G3 H1 H2. Fine. This we can simplify if you take common, but we are not going there. So let us keep it as it is. So let us leave it like that. 1 plus H1 can be taken common, but we are not simplifying. So this is our delta. So now we have to calculate delta 1 as well as delta 2. So what are delta 1, delta 2? So delta of that graph that is not touching the kth loop. So if we consider path 1, P1, we have to consider those loops which are not touching this and then calculate the delta. If we are considering path 2, we have to consider those loops which are not touching that path and then calculate delta for those loops. So for calculating delta 1, are there any loops that are not touching this? Are there any loops that are not touching this?
All the loops are touching, sir.
All the loops are touching. So no non-touching loops means delta 1 is equals to just 1. So delta 1 is 1. Now coming to delta 2. Are there any non-touching loops for this path P2?
L1, L1 and L2.
L1 and L2. Very good. So L1 and L2 are the two non-touching loops that are not touching this path. So for these two non-touching loops, we have to calculate the delta. So delta 2 is nothing but 1 minus summation of individual loop gain, which is minus H1 minus G3 H2 plus product of these loop gains, which is G3 H2 H1. So if I simplify, my delta 2 is 1 plus H1 plus G3 H2 plus G3 H2 H1. Now if I apply the Mason's gain formula, which is my overall gain, which is the transfer function, which is y of s by u of s. Delta is same, so the numerator is same. Numerator I have P1 delta 1 plus P2 delta 2. So my y of s by in u of s is P1 delta 1 plus P2 delta 2 by delta. We have calculated all the values. So now this expression results in the final gain of output from input to output. What is the transfer function? So now this entire thing can be replaced by a single y of s to u of s by a single block whose transfer function is given by P1 delta 1 plus P2 delta 2. P1 is already known, G1, G2, G3, G4. Delta 1 is 1. P2 is G5 and delta 2 is 1 plus H1 plus G3 H2 plus G3 H2 H1 and delta is this expression. So is this clear, everyone? Have we understood?
So delta 2, can you tell delta 2?
Yes, so delta 2. So for delta, what we are considering? Delta, we are considering the entire circuit and then considering all the loops in the circuit. But when we are saying delta k, we have to consider those loops which are not part of that path. So for P2, my path is UAEY. So for this path, are there any loops that are not touching with this and are also non-touching? L1 and L2, these two are not touching this path itself. So now considering these two loops only, I have to recalculate delta because the original delta had three loops and then two non-touching loops, right? L1, L3, L1, L2. But for this delta K, I have to only consider L1 and L2 because these two loops are not touching the path itself. So for this calculation, the delta formula remains the same. 1 minus sum of all individual loops plus sum of product of all combinations of two non-touching loops. Because I have only two loops which are not touching, I'll have delta 2 is equals to 1 minus summation of this plus G3 H2 H1. Say these two are touching, for example, then this third expression will not be there. It will be 1 minus summation of the gains. So we'll have 1 plus H1 plus G3 H2 only. Is that clear?
Delta 2 is equal to 1 minus the gains of the loops which are not touching that particular second forward path, sir.
Yes, yes, which are L1 and L2, right? This minus H1
But
minus G3 H2.
Why we should consider non-touching loops, sir?
Not like, see, when okay, I think I got your question. So
Yes.
the loops that are not touching the forward path.
No, we should not consider the last term, that is
Yes, we cannot
G3.
consider this because E is considered a path of the path.
No, sir. One more thing, sir. That delta, please scroll down to delta 2, sir.
Yes.
That last term G3 H2 H1 should not come, I think, sir.
Why? These two are
1
not,
minus,
these two are non-touching, right?
yes, sir.
So I
Gain,
have to, So please continue.
okay, fine. You are using the delta formula is applicable for delta 1 and delta 2, delta 3, and so on, sir.
Yes. So this delta is applicable for all the delta 1, delta 2, delta 3 up to so on. But for delta, we'll consider the entire circuit. We'll consider the overall circuit. Whereas for delta 1 and delta 2, we'll consider that part of the circuit which is not part of the forward path. So I cannot consider, if I am considering this forward path, I cannot consider any loops that are part of this forward path. So there exists no such loop. So I cannot consider any loop, which means delta 1 is 1. Whereas if I am considering this forward path, then there are two loops which are not touching with this G5. So now using these two loops, which are L1 and L2, and also they are non-touching. So using these two, I have to calculate the delta. So which is 1 minus summation of summation of the gains plus summation of product if they are not touching. Say L1 and L2 are also touching, then this term will vanish. Only I'll get this term. But the calculation remains same.
Okay, sir.
Okay. So similarly, we can do for this problem also, which is again simpler, right? We can take this problem and then we can calculate. So this is simpler only. So we have how many forward paths are there for this problem? I'll consider this. This is example 1. So this is example 1. This is example 2. So how many forward paths are there?
Only one.
One.
One forward path, right? So what is the path gain?
G.
Forward path gain?
G, sir.
G, right? Or
G.
simple G. Okay. And how many loops are there? Loops?
Only
One loop.
One loop. What is the gain of that loop?
Minus BH.
Minus GH.
Minus GH. Very good. So loop, we have one loop and the gain is minus G into H. Very good. So now we'll calculate delta. Delta is 1 minus of summation of all the path gains, which is minus GH, plus product of two non-touching loops, but there are no two loops. So delta is what? 1 plus GH, right? Clear? Delta is clear?
Yes, sir.
Yes,
Yes,
sir.
sir.
Okay. Now what is delta 1? Delta 1, we have to consider those loops which are not part of the forward path. Are there any such loops?
No.
No, sir.
So 1 minus
No,
0,
sir.
which means 1. So now my input to output transfer function, which is y of s by r of s, will be delta 1 p1 by delta, right? Because only one path. So delta 1 is 1, p1 is g. So we'll have g by delta, which is 1 plus gh. So this is what we have formulated, right? Clear?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
Okay. So if you have any doubts until this point, you can ask, else we can solve one problem. So let me draw the problem. I'll consider the same problem what sir has considered. So it is just to apply the knowledge, but any such given problem, you have to do the same. So let me draw the block diagram. And there is less than a minute. So if this meeting ends, kindly join back. So is the pace of discussion okay, or should I increase or decrease? Any comments? Pace is fine, or am I going too fast or too slow? Or am I repeating
Fine, sir.
too much?
Fine, sir. No.
Fine, fine. Okay. If you give feedback now, then I can change accordingly, else things can go in a different direction. Okay. If the pace is fine, then it's okay. So H1 and then this is plus minus. So the meeting might end anytime soon. So if this ends, kindly join back, then we can solve this problem. Let me quickly draw the diagram. One. Okay. So this is the oral circuit diagram. Sorry, there is G5 also. So G5 is from here. Okay, so this is again plus sign. So we were asked to solve this input to output transfer function using the block diagram reduction. One way is to reduce the block diagram itself. We can play with the block diagram and then we can get the details. Another one is to use the Mason's gain formula, which we have discussed. So let us start with the block diagram reduction. So anyone how to use this block diagram reduction technique and do any idea or so this is the given question, right? So let me not touch it. Let me just redraw it. And now let us use the block diagram reduction technique.
First
So
having
anyone?
the summing point before the G3, sir.
Yes, very good. So we can move the summing point before the G3. So what I will do is I will erase this point. Okay. And then I'll remove this gain and then I'll take it from here. Okay. Maybe I'll use a different color so that we'll know what we have changed. Okay, let me use orange color. So here I am changing the gain. I have, okay. So previously I was taking from here, which was already multiplied by G3. So now if I'm taking from the previous value, what will be this gain? H2?
1 by G3.
1 by G3 or if you have any confusion, always the best thing is to take, say this value is X. Then this value is G3 into X. And this will be H2 G3 into X, right? So now the same value, this value is I am taking as X. This should be G2 H3 into X. So what will be the gain? Anyone?
1 by G3 H2X.
If this is X, output is G2 H3 into X. What will be this gain?
G3
Sorry,
into H2.
G3 H2, right? Sorry, my bad. G3 into H2, right?
Yes.
Not 1 by G3.
Yes, sir.
Okay, is that clear for everyone? Hello. This is clear, right? Straightforward. G3 into H2. Now, I can see two feedback loops. So, uh, so this is one negative feedback. This is one another negative feedback, right? Agree, everyone?
Sir,
So now I can simplify these gains. So what will be the gains? Can anyone tell me? If I redraw, what will be those gains? So this is that gain block that is modified. And then we have G3 and G3 and G5 can be added, right? So this is G3 and G5. So that also I'll try to add. So it will be G3 plus G5. So we have this as well. So this also can be added. So this block will be added, and then this block will be added, and then R of S. And then there is unity gain, Y of S. So the gain is 1. This is plus minus, this is R of S. Okay, so now what will be the gains? Can you tell me? What will be the simplification of this? What will be the simplification of this? And what will be the simplification of this? Anyone? If G2 is the forward path, G3H2 is the reverse path.
Sir, first one G2 divided by 1 plus G2 G3 H2.
Very good. Next one,
Next one G3 plus G2. Sorry.
G3 plus G5, right?
G3 plus G5.
Yes, very good.
Third one G4 divided by G4 H1.
1 plus G4 H1. Very good. So now we have simplified the given block diagram into something like this. So now for my simplification, what I will do is I'll consider this entire thing as G. So what I'm going to consider is I'll consider this entire part G, which is G1 into this second, third, fourth part product. So now I have simplified G, Y of S, part gain is 1. This is R of S. This is plus minus. The gain is 1 here. So now what is Y of S by R of S? Where my G is
G divided by 1 plus G.
G divided by 1 plus G. So here my G I am writing it is G2 by 1 plus G3 G2 H2 into G3 plus G5 into G4 by 1 plus G4 H1, and my overall will be G by 1 plus G. Okay, so now what happened is I have made some change in the block diagram, and then luckily I got to reduce it, and then finally I got the overall transfer function. What happens, say if this thing is not possible, say what if I could not move this from here to here, and then say no such block diagram reduction is possible, then we can't do anything, because then we cannot reduce the block diagram, right? So then we have to forcefully go for the Mason's gain formula. So let us also do that. So the first method we have done is block diagram reduction. Now let us do Mason's gain formula. So any doubts in the block diagram reduction, anyone? Before we go to Mason's gain formula? Any doubt, anyone? Okay. So if you don't have any doubt, let us start. First, we have to draw the signal flow graph, right? So now let us assume this. Let us assume this is A, this is A, this is B, this is C, this is D, this is E, this is F, and this is G. So these are the nodes that I have considered. So RFS to YFS, these are the nodes. So let us write it. So we have R of S, A, B, C, D, E, F, G, and Y. Okay. So let me name those also. So we have R of S, here Y of S, then we have A, B, C, D, E, F, and then G. So from R of S to A, we have a gain of 1. A to B, we have gain of G1. Then we have G2, then we have G3, then we have again gain 1 because it's a summer block. Then from E to F, wait, I think I have messed up a little bit. So from A to B, we have G1, B to C, we have gain 1. And then from C to D, we have gain G2. And from D to E, we have gain G3. And from E to F, we have gain 1. From F to G, we have gain G4. And from G to Y of S, we have gain 1. Now H1 is from G to F. So this is my loop, which is minus H1. And minus H2 is from E to C. Right, which is minus H2. Right. So anything is missing. G5 is missing, which is from D and it is getting added to F. So from D to F, we have G5.
And G to A, sir.
And G to A. So it is getting added at A, which is 1. So G to A. So from this gain is minus 1. So this is our overall signal flow graph. Is this clear, everyone? How we have drawn? Because this should be clear. If this is not clear, then we'll not be able to solve the problem itself. So how to draw the signal flow graph, is this clear? How I have named the signals that will become the nodes, and then I have connected all the points.
Yes, sir.
Okay, others, what about others? I only hear from one person.
Yes, sir. No problem.
Okay. So now how many forward paths? Again, the process remains same. Forward paths, loops, non-touching loops, delta, delta 1, delta 2, delta 3. So let us start with the forward paths. How many forward paths are there?
2.
Okay. Forward paths. Can you mention the nodes in those 2 forward paths?
A, B, C, D, E, F, G.
Okay.
A,
Second one?
B, C, D, F, G.
A, B,
C, D,
F, G.
F, G.
A, B, C, D, F, G. Very good. So path 1 gain, P1 is what? And then P2 is what?
P1, G1, G2, G3, G4.
P2?
And P2, G1, G2, G5, G4.
G5, G4. Very good. So others agree with what this person has said?
Yes, sir.
There are 2 forward paths and these are the path gains, P1, P2. So our N is equals to 2 basically. So from here I can say N is equals to 2 because there are 2 forward paths. So we need to calculate delta 1, P1, delta 2, P2 and delta. Okay. So if these things are clear, let us see what are the loops in this path. So how many loops are there? Who can tell?
3 loops.
3 loops, which are?
Yes,
A, B, C, sorry, C, D, E, C, loop 1.
Okay,
F,
C, D, E,
G,
C.
F.
Okay, let us just write it so that there will not be any confusion. So loop 1, C, D, E, C, right?
Yes, sir.
Loop 2,
F, G.
F, G. Very good. Loop 3,
A, B, C, D, E, F, G, A.
A. Very good. So loop 3, A, B, C, D, E, F, G, A. Okay. Are there any other loops?
No, sir.
There is
No,
this
sir.
loop, right? A, B, C, D, F, G, A.
Yeah.
This is also a loop, right?
Yes, sir.
Yeah. So L4, A, B, C, D, F, G, A. So just I'll just highlight and I'll erase so that we can see what are the 3 loops. So I'll use blue color. So this is my one loop. And then the second loop is this one. And then the third loop I am using this color. This is the third loop. Fourth loop I am using red color. And I'll erase this. Fourth loop is this loop. So loops are clear, right? Loops can be seen. So that I'll erase. I am just highlighted so that it is visible. So let me quickly
Yes, sir.
erase if things are clear. So these are the loops. So now let us find the path gains of these loops. So can you tell for each loop what is the path gain?
Minus G2, G3, H2.
Minus G2, G3, H2. Minus G2, G3, H2. Okay.
Minus G4, H1.
Minus G4, H1.
Minus G1, G2, G3, G4.
Minus G1, G2, G3, G4. And the last one?
Last one. Minus G1, G2, G5.
And G4.
G4.
Yeah. So is it clear till this point? Everyone minus G1, G2, G5, G4. We have identified two forward paths, but we have identified four loops. And here it is a little tricky, the fourth loop to be seen, but we have gotten it clear and I have also showed. So path gains of the loops are also found. So is this clear until this point, everyone? Forward paths as well as loops. So now can you tell me which of these are non-touching loops?
C, D, E, C and F, G.
C, D, E, C and F, G. Very good. So there are only two non-touching loops, which are, I could say, L1 and L2. So what is the path gain product of these two? L1 and L2?
Sir, kindly scroll down and show the signal flow graph, sir.
Oh, sorry. Now can you see?
Yes, sir. Yes, sir.
So this loop gain product of this, which is minus minus will become plus G2, G3, H2, G4, H1. So I can read it as G2, G3, G4, H1, H2, which I also can multiply from here. These two are not touching loop, right? So G2, G3, G4, H1, H2. So is it clear till this point?
Yes, sir.
Okay. So before we calculate delta 1, delta 2, let us calculate delta. So can anyone tell me what is delta? The expression?
1 minus
1 minus
sum
of these loop gains, right? So minus
loop gains
G3, H2 minus G4, H1 minus G1, G2,
G1, G2,
G3,
G3,
G4 minus
minus
G1,
G1,
G2, G5, G4.
G3
Now minus or plus?
plus
Plus G2, G3, G4, H1, H2. So this is what we have obtained. Let us put in a box. Okay. So now P1 and P2 are known. So now we have to find delta 1 and delta 2. So for calculating delta 1 and delta 2, first we have to identify the loops that are not touching the forward path. So are there any loop that are not touching this path, first path?
No, sir.
No. So what is delta 1?
no 1
Delta
1.
1 is 1. And let us check delta 2. Are there any loops that are not touching this forward path P2, which is A, B, C, D, F, G?
No, sir.
No. So what will be delta 2?
It's also
1.
1.
Delta 2 is also 1. So delta 2 as well as delta 1 both are 1. So my overall output transfer function input to output is y of s by what is the input, r of s or u of s? R of s. Y of s by r of
R of
s
S.
is p1 delta 1 plus p2 delta 2 and both are 1 by delta. So this will be the overall input to output transfer function. If you see here, it may look simpler given that we were able to minimize the block reduction. Say what if we could not push this here, say there is some other summer block here, then it is not easy to push it, then we cannot solve everything by block diagram reduction. In this circuit it happens to be solved by block diagram reduction as well, but in such cases where it is not possible, then we have to use this formula. The best thing about Mason's gain formula is you will get the expression for numerator as well as denominator, whereas here if you see, you have to multiply all these things and then do g by 1 plus g. You have to do the math, right? I have not done it. I have just represented in terms of g. Whereas in the Mason's gain formula, I have gotten the expression denominator as well as numerator. So I can get the overall expression without actually solving by just using the loop gains. So this is simpler in that way, but there can be instances where block diagram reduction can be simpler. But it does not always mean that you can solve all the problems by block diagram reduction, whereas you can solve all the problems using Mason gain formula, and it is systematic. It is not, you know, difficult. The method is simple. You have to understand the terminology. You have to follow the same exact path for all the questions. Only the difficulty will be, or the mistake that you may make is drawing the signal flow graph and seeing the number of loops as well as forward paths. If you don't make any mistake till that point, then you will not be making any mistake until you get the solution. So the method has to be clear, and we should not make any mistakes. So is this clear until this point?
Yes, sir.
Okay. So once this is clear, then let us solve one problem. So now what I'm asking is construct the signal flow graph for the circuit shown below. So the circuit shown I will draw. So I will consider one RLC circuit. So say resistor we have, and then here I will consider inductor, and here I will consider another resistor. Here I will consider capacitor. Okay, so this is my input plus minus. So my input is say V in of S. Okay, this is my I1 of S, and this is my I2 of S. Okay, say the resistor, this is 1 ohm, this is 1 ohm, this is 1 ohm, and capacitance is say 2 farad, and inductance is say 2 Henry. Or let us consider this a different. So let us consider 5 ohm. 5 ohm. Now the signal flow graph is asked in such a way that my points are V in of S, I1 of S, and I2 of S. So this is my V in of S, this is my I1 of S, this is my I2 of S. So whatever connections they are going to have, feed forward or feedback, whatever connections they are going to have, we need to find those and draw the signal flow graph. Okay. So, but we were told that I1 of S as well as I2 of S are the node points. So now using those, we have to draw the circuit. Let us draw. But first, everything should be in S domain, right? So if I consider 2 Henry inductance into S domain, what will be the S domain for inductance in S domain? Anyone? Resistance is
Yes.
R in both. What about inductance?
S into
LS.
L.
S into L, right? So I'll consider this as 2S. What about capacitance?
1 by
1 by CS.
1 by CS. Very good. So 1 by 2S. So now I have to write my I1 of S in terms of V in of S as well as I2 of S. Similarly, I have to write my I2 of S in terms of I1 of S and V in of S. Here my V in of S is the input. Okay. So now we have to write down the equations and then we have to find. So can anyone tell me what will be this current in the inductance?
I1 minus I2.
I1 minus I2. Very good. So now let me assume that this voltage V dash of S. Now what is V dash of S from V in of S? Using V in of S, what is V dash of S?
L into DI.
Yes. So one is 2S into I1 of S,
D by
I2 of S. I am writing everything in S domain, so there is no d by dt. So that is one advantage that we have discussed for Laplace transform. Everything is in S domain, so there is no confusion as such. Is that clear?
yes, sir.
Okay. Now similarly, in the exact same way, I can get from V input also, right? What is my V dash of S? V dash of S is V input of S minus I1 of S. Agree?
Yes, sir.
Okay. So now say I want I1 of S in terms of V in of S as well as I2 of S. So now what I will be doing is I can substitute V dash of S in this equation, right? I can do.
Yes, sir.
Okay. So let us substitute this equation in this expression. So now I will get my V dash of S, which is equals to 2S into I1 of S minus 2S into I2 of S is equals to V in of S minus I1 of S. So now if I bring I1 of S one side, I'll have I1 of S into 2S plus 1 is equals to V in of S plus 2S into I2 of S. So now if I bring everything onto the right side except I1 of S, I will have I1 of S is equals to 1 by 2S plus 1 into V in of S plus 2S by 2S plus 1 into I2 of S. Is this clear? This is my equation 1. So basically, what I have to do is I have to calculate I1 of S in terms of V in and I2 of S. Similarly, I have to calculate I2 of S in terms of V in and I1 of S. Then I can draw the signal flow graph. So one equation I got was I1 of S in terms of V in and I2 of S. So now let us do the next one. So V dash of is what? 5 plus 1 by 2S into I2 of S. That also is true, right?
Yes, sir.
Right?
Yes,
Yeah. So V dash of S, which is equal to this, we also have another expression, which is V dash of S is 5 plus 1 by 2S into I2 of S. Everyone agree? Now what I'll do is I'll substitute this in this equation. So on the left hand side, we have 2S into I1 of S. So I have 2S into I1 of S minus 2S into I2 of S on the left hand side is equals to 2S into 5, 10S plus 1 by 2S into I2 of S. So now what I will do is I will bring I2 of S one side, I1 of S on the other side. So let me simplify. I'll have 2S into I1 of S is equals to 2S plus 10S plus 1 by 2S into I2 of S. So if I simplify it, I'll get 4S square plus 10S plus 1 by 2S into I2 of S. So now if I simplify, I will get I2 of S is nothing but 2S into 2S, it is 4S square by 4S square plus 10S plus 1 into I1 of S. Is this clear? I have just solved and then calculated I2 of S in terms of I1 of S. Is that clear?
Yes, sir.
So now let me redraw it. So I have V in of S, I have I1 of S, I have I2 of S. So this is my V in of S, and this is my I1 of S, and this is my I2 of S. So first let us draw for I1 of S. I1 of S has one component from V in of S. What is the gain of that?
One by
What is the
2s
gain?
plus 1.
1 by 2S plus 1. Very good. So this is 1 by 2S plus 1. And another component from I2 of S. What is the gain of that?
2s divided by 2s plus 1.
2S divided by 2S plus 1. So I'll have another component from the top, which is, let me put this down. So this is 2S divided by 2S plus 1. So now I have to calculate I2, which is direct path I1 to I2, and the gain is given by 4S square by 4S square plus 10S plus 1. So basically what they have done is they have given an RLC question and they have given the nodes also. And they are asking to find the or draw the signal flow graph for that. So what I have done is I have converted everything into S domain, and I have seen if I want to calculate I1 of S and I2 of S, I need one equation of I1 of S in terms of V in of S as well as I2 of S. Similarly, I2 of S I need in terms of V in of S and I1 of S. But here I have applied one KCL. I have assumed V dash of S. So I got three equations. V dash of S I got in three different forms. I have substituted one in one equation and one in another equation to get two equations, and then from there I have drawn the signal flow graph. So this is my overall signal flow graph. Is this clear, everyone? Hello.
Yes, sir.
Okay. So in this case also, if I ask, say my output is I2 of S, then I'll have my gain this one. So I can ask another question, what is my I2 of S by V in of S? So what is this transfer function? So this can also be asked. So this is another such question that can be asked as well. So in this case, you have to apply the Mason's gain formula for this one, and it is also simple and straightforward. So I'm not solving this. This is what I have saying that this can also be asked. So I think at this point you should be able to do this, and I think it is clear as well. So this completes Mason's gain formula. Before we go into time domain characteristics, any doubts, anyone?
Sir, I have one doubt, sir.
Yeah, please ask.
We are using Mary's gain formula. We are using the block of gain block and in forward feedback.
Sorry, can you please repeat? Your voice is a little bit slow.
Yeah, sir. In signal flow graph sums, we are using
Yes.
gain block as well as forward loop gain or H and G only, na.
Yes,
But
gain.
here we are using Laplace transform in the terms of Laplace equations, S
Yes,
domain.
yes.
If we are solving this signal flow graph using Morris gain formula, sir,
Yes,
is
you
that
can use.
possible?
Yes. So if you see here, I have mentioned gain as G1, right? But this gain
Yeah.
is not a constant. This gain is G1 of S. This is G2 of S. This is G3 of S. This is G4 of S. This is G5 of S. This is minus H2 of S. This is minus H1 of S. So all are in S domain because these are blocks, right? For simplicity, we have removed the S. Similarly, here also, what we can do is we can consider this as G1 of S, G2 of S, H1 of S, and this is 1. So we can still apply the same concept there as well without any issue.
Thank you, sir.
Okay. So if there are no more doubts, then we can move to time domain analysis. And what is time domain analysis? Basically, we are finding the step response, impulse response of a first order system, and then we'll see what is its time domain expression. So now first order systems are simpler, but when we go to the second order system, there are different type of systems. We'll also look into that. First, let us start with a first order system. So let me consider the block diagram of a system which has a transfer function of 1 by tau s with a negative feedback. So this is my y of s, this is my u of s. And so there is a negative gain minus 1, gain 1. So now what is my y of s by u of s? What is my y of s by u of s? Anyone? If we solve for this, this is a unity negative feedback system.
One by 1 plus tau s.
1 by 1 plus tau s, right? So how did we get 1 by tau s by 1 plus 1 by tau s? So I got 1 by 1 plus tau s. Actually, my writing pad is creating issues today. It is disconnecting and connecting again. So that's why this is caused. Okay, so this is the overall transfer function. So now let us consider two inputs. First input is impulse input, which means my u of s is 1, right? Agree? Impulse input means u of s is 1, right? Impulse transfer, Laplace transform of impulse input is 1. We have studied, right?
Yes, sir.
So now my y of s is 1 by tau s plus 1. So now can I calculate y of t from here? Using the knowledge that we have learned last week. How can I do? First, what I'll do is I'll take tau common in the denominator. So I'll have s plus 1 by tau. So from this, can I calculate y of t?
E power minus 1 by tau t.
Yes. So there is also 1 by tau in the front and then e to the power minus t by tau, right? So can anyone tell me what is steady state error at t tending to infinity? So what is limit t tending to infinite y of t value, which is also like y steady state? What is this value? Anyone?
0, sir.
0. Yes, very good. So this is for impulse input. Now let us see what will happen if we give unit step input. Again, there is less than a minute. So if this meeting ends, kindly join back. So this is unit step input. So for that, what is u of s? U of s is 1 by s. So now let us calculate y of s. I'll just quickly do because it is simple math. So we'll have 1 by s into tau s plus 1. If I take tau common in the denominator, I'll have 1 by s into s plus 1 by tau. So this is nothing but 1 by s minus 1 by s plus 1 by tau. If this meeting ends, kindly join back. So y of t is nothing but 1 minus e to the power minus t by tau. So here I got a different expression. Here I got a different expression because input is different. So now in this case, what is my limit t tending to infinite y of t expression, y of t value, which is y steady state of t?
One, sir.
1. So input if it is step, output is also at the steady state it is reaching 1. So for a unit step input, if we see the response, so it will be something like this. Say my input is like this. Say it is started from 1. And say this is unit step. So this is my input. Then my output will look something like this. It's a first order response. It will reach the input at time t tending to infinite. So this is my u of t, and this is my y of t. So that's how the output tracks the input and it reaches the input value. So this is for the first order system. So now, if the concept is clear, let us quickly solve the one problem on first order system. So consider an RC circuit where the capacitor voltage is the output. So first let us find the transfer function, and then we have to find the impulse response of the system. So I have considered one RC circuit. This is resistor and this is capacitor. Let us maintain in terms of R and C to maintain the problem generic. This is my VN plus minus, and this is R. This is of course 1 by CS, and say this is my input V of S, and this is V naught of S. So first we have to find the transfer function. So what is V0 of S by V of S? Anyone?
One divided by one plus SCR.
Very good. So it will be 1 divided by 1 plus SC into R. So this is the transfer function. Now I am asking what is the impulse response. So what in that case, what is V in of S?
1.
1, right? So V in of S is 1. So now what is V naught of S? V naught of S is whatever that is left. V naught of S is 1 by 1 plus SC into R. So now can I find the V naught of T? How to find? I have just done in the previous slide. So how to do? Anyone?
E power minus
Take is common.
T by CR.
Yes, someone said e to the power minus t by cr. It is partially correct. So what we are going to do is v naught of s, right? I will take in the denominator rc as common. Then I'll have 1 by s plus 1 by rc. So now if I apply inverse Laplace transform, I will have v naught of t is equals to 1 by rc into e to the power minus t by rc. So this is my overall final expression. So this is the capacitor voltage for the impulse response. If I give unit step, then there will be 1 by s term. Similarly, we'll have two terms as how we have solved previously. So this is how we have to solve the first order systems. So is this clear? First order systems, how we are calculating the response?
Yes, sir.
Yes, sir.
Okay. So if you don't have any doubts, now we can go for time domain analysis of second order systems. So we'll consider one generic second order system and then see what type of what type of systems we can get, and based on that how we can solve a given problem. And here, what are the parameters that we can get and how the response looks like. So let me quickly draw the diagram. Omega n square by s into s plus omega n. So this is a generic second order system that we are considering over here. So can anyone tell me what will be the transfer function y of s by r of s? Sorry, this is not the generic one. I made a mistake. It will be s into s plus 2 zeta omega. Okay, so can anyone tell me what will be the transfer function, final transfer function for this unity feedback system?
Omega n square by s into s plus.
Omega n squared by. Just a minute, my writing pad is creating issues. I'll just remove and connect it back. So omega n square by s square plus 2s zeta omega n plus omega n square. Yes. So now here there are certain nomenclature again. Let us see what is that. So starting with omega n, it is called natural frequency. And then there is zeta. It is called damping ratio. And then there is something called omega d that we don't see on this like page, but it is called damping frequency. Okay. Now zeta can have different values. Based on zeta, we'll see what the system is called zeta. So there are 4 cases. Okay. So the first case, zeta is greater than 1. Let me remove the 1. So we have 4 cases. Zeta is greater than 1. 0 is less than. Then zeta is equals to 1. Then 0 is less than. Zeta is less than 1. Then zeta is equals to 0. So depending upon the damping ratio, the system's performance can vary. Okay. So zeta less than 1. Sorry, zeta greater than 1 is called overdamped system. This is called critically damped. This is called underdamped. And this is called undamped. So I hope you have followed sir's lectures, and I think It is clear till this point. And also one thing, damping frequency omega d is nothing but omega n into square root of 1 minus zeta square. So this is how it is defined. And these are the different type of damping the system can have depending upon the zeta value. Let us see how the step response will look like for each of them. So let me consider one gray color would be good. Yeah, gray color. So this is my input. I call this u of t. This is my u of t. So first starting with overdamped. Overdamped response will be looking mostly like a first order system. So it will look like this. So this is my overdamped case. And then coming to critically damped. How will my critically damped look like? Critically damped will look like something like this. So this is critically damped. And then how will my underdamped system will look like? It will look like something like this. It will have some oscillations which will dampen. So this is my underdamped system. And undamped means it will have oscillations. So it will look like something like this. It will have oscillations. Okay. So this is my undamped system. So depending upon the damping, the system's dynamics can change. So that's why damping will play a very crucial factor. And omega n is the natural frequency. And depending upon this zeta as well as omega n, that also will decide how quickly the uh, oscillations will damp out, if at all there is damping. Else, then there will be fully oscillations like in undamped case, where it is not having any damping. So the oscillations are there forever. Whereas in the case of underdamped, there are few oscillations. Critically damped and overdamped, there are no oscillations. So is this point clear until this point? Is the concept clear until this?
Yes, sir.
Okay. So now, before we go into steady state error, that is another concept. So for unit step response, so for unit step response. Okay, so there are certain terminology that we have to learn. One is the rise time. So one is the rise time. Rise time means the output has reached from 10% of the final value to 90% of the final value. And this is defined as TR is equals to pi minus cos inverse zeta by omega d. So this is my rise time. Then there is peak time. Peak time means in the case of under damped case, the time it has reached to the time it has taken to reach this peak. So this is the peak where the peak is happening. So time to reach peak. Time to reach peak. So this is given by Tp, which is equals to pi by omega d. And then there is maximum percentage overshoot, which is MP. How much is the peak? Peak overshoot. This is called peak overshoot. In percentage. So MP is equals to 100% into e to the power minus pi zeta by square root of 1 minus zeta square. And then there is another term called settling time. This is called settling time. And it is defined as Ts is equals to 4 by zeta omega n. So these are certain formula that you have to remember for a second order system. Depending upon the damping as well as the natural frequency, these can vary. So these are certain terminology that were discussed. So is this clear until this point, everyone?
Yes, sir.
Okay. So let us solve one problem quickly. So consider a unity negative feedback system illustrated below. So G of S is given, H of S is also given. So let us quickly draw the circuit, how it looks like. So this is my G of S. And this is my H of S. And this is my R of S. This is my Y of S. And it's a unity negative feedback system. So now what is the overall transfer function? Y of S by R of S?
100 divided by
100 divided by
s square plus 4s plus 100.
S square plus 4S plus 100, right?
Yes, sir.
Okay, very good. So now can you calculate what is the natural frequency of the system? What is omega n?
10.
10. Very good. What is zeta? Anyone? What is zeta? Or I would say what is 2 zeta omega n?
0.2. Zeta
What is
0.2
2 zeta omega n?
4.
4. From this can you calculate zeta?
That is 0.2.
0.2. Very good. So now tell me whether the system is overdamped, underdamped or critically damped. Anyone?
Underdamped.
Underdamped.
Underdamped. Very good. So the system is underdamped because zeta is lying between 0 and 1. And how much is the natural frequency of the system?
10 radians.
10 radians per
Percent.
second. Very good. And what is the damping ratio that we got? Point 0.2, right? We have just calculated the damping ratio zeta. Yes or no?
Yes, sir.
Now, what is the damped natural frequency, which we have already defined, which is given by omega d, which is nothing but omega n into square root of 1 minus zeta square. So can anyone tell me what will be the omega d? Once you calculate, can you let me know what is omega d?
Nine 9.79.
9.79 radians per second. So you got 9.79. I hope others are also getting the same value. It is 9.79. So now I am asking rise time, peak time, maximum overshoot, as well as settling time. So let us see. I'll just copy paste. We can use the same formula. So please calculate one by one and let me know what is the rise time, what is the peak overshoot, what is the peak time, and what is the settling time. So we can start with the rise time. So let me know what values you got. I'll note down here. So what is the rise time that you got? What is the peak time that you got? What is the maximum peak overshoot that you got? And what is the settling time that you got? Anything, anyone, you can calculate, or maybe we all can start with the TR, TP, MP, TS. Let me know one by one so that I will calculate. I don't have the answer. So you please calculate and let me know what value you are getting. So once you have calculated anything, please let me know so that I'll write the answer and others can cross check. So has anyone calculated anything?
Sir, peak time
Okay, how much did you get?
0.32.
0.32 seconds. Okay. Let us see whether others got the same answer. And please calculate the other values in the meantime.
Settling time 2.
Sorry.
Settling time
Settling time is
2.
2. Yeah, very good. Settling time is 2 seconds. Zeta omega n is 2. So 4 by 2 is 2 seconds. So peak time is 0.32 and settling time is 2. Let me write over here. Peak time is 0.32 and settling time is 2. Okay. So now maximum percentage overshoot as well as rise time. Rise time is pi minus cos inverse 0.2 by omega d. Omega d we have already calculated, I think 9.76, 9.79. So yeah, please calculate and then let me know the answer.
The peak overshoot is 52.66.
52.66 percentage. Okay.
Yes, sir.
And then rise time. So if this is the value, just let me write down here 52.66.
The rise time is 10.15 seconds.
10.15. Is that correct
Yes.
or?
I'm I'm having some doubts, sir, but I calculated.
Because I guess rise time is 10% to 90% of the final value, right? It should it be less than peak time? So that is
Yes.
my question. Just check, because pi by omega d is bigger than rise time, right? It is pi minus cos inverse zeta by omega d, means it is smaller than peak time. So it should be less
Yes.
than 0.32. Just cross check your calculation once.
Okay, sir.
Sir, can you tell me what is omega d?
Sorry, your voice is very low. I can't hear anything.
Sir, omega d. May I know the value of omega d or formula?
Yes. Omega d is square root of 1 minus zeta square into omega n, and omega d is 9.79.
Okay, sir.
So can you get anything from this? Okay. Yeah, if someone does it, please let me know the rise time. Then we can solve.
Sir, if we are using calculator,
Your voice is very low. Sorry, I am not able to hear anything.
sir, if we are using calculator
Yes.
in that pi in radian mode or degree mode?
Pi in radian. 3.14 minus cos inverse zeta, that also in radian, by omega d. I don't have a calculator right now, else I would have calculated. Else we can leave it at this point. It is just a calculation that you can do. Just cos inverse zeta has to be in radian mode,
2.18,
because, sorry,
sir. 2.18.
but it should be less than TP, right?
So we were getting 0.18, sir.
0.18. Oh, I heard 2.18. Okay, my bad. 0.18. Okay, I think this is correct because it is less than TP. Yeah, so these are just the calculations that you can do. You just have to be careful with the calculations. But I think the concept is clear, 0.18 seconds. So if the concept is clear, I'll move to the last topic of today, which is the steady state error. Any doubts until this point? We'll just quickly brush up this and then we'll move to the final problem
Fine,
for today's
move.
session.
Yeah, sir,
Sorry?
you can move.
Okay.
Yes, sir, yes, sir, you can move.
Okay, no problem. So in the steady state error, basically we discuss about the steady state error of the system. So let us consider the same negative feedback. So it can be of any order: g of s, y of s, h of s, r of s, h of s. Say plus minus. And this is error of s, e of s. So now we know y of s is nothing but g of s by 1 plus g of s, h of s into r of s. And we know that error e t tending to infinite is nothing but limit s tends to 0, s into e of s. Agree, everyone? I am applying the final value theorem. So limit t tending to infinite, e of t is nothing but limit s tending to 0, s into e of s. Agree,
Yes,
everyone?
sir.
Yeah.
Yes.
So now s tending to 0, s into e of s is nothing but r of s minus y of s. So if I take r of s common, then I'll get 1 minus g of s by 1 plus g of s, h of s. So let us consider it is unity feedback. So h of s is equals to 1. Then if I simplify, I'll get E steady state of s of t is nothing but limit s tending to 0, s into r of s by 1 plus g of s. So this is what we will be getting. Now let us consider three cases. First case being unit step input. Unit step input. So in this case, what will be my R of S? My R of S is nothing but 1 by S.
1 by S.
Yes. So now if we simplify it, we will get E steady state of T is in the form of 1 by 1 plus Kp, where Kp is equals to limit S tending to 0, G of S. And this is called position error constant. Position error constant. Similarly, if I go to unit ramp input, then my R of S is 1 by S square. So if I substitute that, R of S is 1 by S square, then we'll get one S in the denominator. Then if you simplify, you'll get ESS of T is nothing but 1 by KV, where KV is equals to limit S tending to 0, S into G of S. So this is called velocity error constant. So it is named like that. Position, then velocity. Now let us consider unit parabolic input. Which means R of S is 1 by S cube. So in this case, E steady state of T will be 1 by Ka, where Ka is nothing but limit S tending to 0, S square into G of S. So it is all simple and straightforward. So this is called acceleration error constant. So we have derived from our existing knowledge of the final value theorem, and we have calculated error in terms of input and output. We have assumed that H of S is 1 unity feedback. Then we have gotten what is the error for step input, ramp input, as well as parabolic input. So this is simple and straightforward, and how we calculate the steady state error. So now, using this knowledge, let us solve one problem quickly. So again, there are different types of input. One is the type 0 input, another is type 1 input. So what is type 0 and what is type 1? So the G of S forward path, if it has one pole at origin, it is type 1. If it has 0 poles at origin, it is type 0. If it has more than one pole, then it is more than type 1. So the number of poles at origin is its type. So if it has 2 poles at the origin, it is type 2. So if it has 4 poles at the origin, it is called type 4. So what is G of S here? Type 0 or type 1?
Type 1, sir.
Type 1, right? Because it has 1, 0. So that's why it is type 1. Okay, previously we have derived the steady state error for H of S equals to 1. But in this question, H of S is not 1. So let us rederive it again. Okay. So we have error of S, G of S, Y of S, H of S, then negative, R of S, then this is E of S. So let me quickly derive. First, what is E of S? E of S is nothing but R of S minus H of S into Y of S. I think I have made a mistake. There is one H of S here. Previously, I think I might have forgotten. So yeah, R of S into here, H of S is also there. So my bad. So this is not 1. This is H of S. R of S into 1 minus H of S into G of S, because H of S is multiplied, right? In the feedback, it is not just Y of S. Okay, that's okay. So let us write R of S minus H of S into Y of S, which is R of S minus h of s into g of s by 1 plus g of s h of s into r of s. That means E of s is equals to r of s by 1 plus g of s h of s. Now for b, let us solve b first. B is nothing but limit error. This is nothing but limit s tending to 0 s into r of s by 1 plus g of s h of s, right? So what is r of s in this case?
1 by s.
1 by s. So 1 by s and s will get cancelled. Limit s tending to 0. We have 1 by g of s into h of s is 10 by s into s plus 2 into s plus 5. So 1 plus 10 by s into s plus 2 into s plus 5. So what is the steady state error in this case? If I substitute s equals to 0, what I will be getting?
1.
S equals to 0. So it will be 10 by 10, which is 1 by 1 plus 1, half, right? 0.5, right? Sorry, not 0.5. This is 0, right? This term is tending to infinite. So this term is tending to infinite.
1 by 1, answer is
1 by infinite. So it is 0, right? The denominator is tending to infinite, which means it is 0, right? Agree?
Sir, 1 by 1 plus
1 by 1 plus infinite, right?
1, anything by 0.
This is 10 by s into s plus 2 into 1 by s plus 5, g of s into h of s, right? So 10 by s into s plus 2 into s plus 5, which is infinite, right? When s equals to 0, this is infinite, right? This denominator is 0, which means this is infinite.
Yes, sir.
So 1 by infinite means 0, right?
Yes, sir.
Yes.
Clear? Okay. So let us solve another problem, which is for the ramp input. I have asked for unit step input and unit ramp input. So for ramp input, R of s is 1 by s square, right? So E of 1 by s, so there is one denominator in the, there is one s in the denominator. So we will have 1 by s plus 10s by s into s plus 2 into s plus 5. So if I substitute s equals to 0, first this and this get cancelled. So then I'll have 1 by 10 by 2 into 5. So this is 1. So in this case, steady state error is 1. Previous case, it is 0. So E steady state. There is less than a minute. If this meeting ends, kindly join back. If you have any doubts, we can clarify. And again, this is the last problem. Once your doubts are clarified, I'll just summarize this session and we'll wind this session up. So once this meeting ends, please join back. I'll summarize the session. Until then, any doubts? So steady state error means we have to calculate E of s and then using the final value theorem, which is E steady state of t is limit s tends to 0 s into E of s. But if my R of s is unit step, then it is 1 by s, else it will be 1 by s square. So depending upon the input, my error will change, of course, and depending upon the type of the system. And type is nothing but the forward path, how many poles are at zeros, that defines the type. Here there is one pole, so it is type 1. Any doubts until this point?
No, sir.
If you do not have any questions, let me just quickly summarize what we have discussed today. So today we have discussed about block diagram reduction as well as the time domain characteristics. So first we have understood what is signal flow graph, because in order to apply Mason's gain formula, we need to understand what is a signal flow graph. So we have started with signal flow graph. We have understood what is node and branch, and then we have understood how to convert a given block diagram into signal flow graph. Then we have understood the nomenclature in a Mason's gain formula, which is input node, output node, path, forward path, loop, and non-touching loops. Then we have understood Mason's gain formula, and we have considered one problem where we have discussed about forward paths, loops, non-touching loops, and how to calculate delta, pk, delta k, and apply Mason's gain formula to get an oral understanding. Similarly, we have done the same for the unity feedback system. Then we went to block diagram reduction using the block diagram reduction as well as Mason's gain formula. So we have started with another example where we have considered block diagram reduction, and then we have also converted that into signal flow graph and applied Mason's gain formula. Anyone is saying something? Palan Kumar, are you saying? Okay. Then we have considered another question where RLC circuit is given and the nodes are given, and then we were asked to draw the signal flow graph. So we have to convert whatever node points are there in terms of other node points, and we have gotten the signal flow graph. Now, if someone asks what is the output to input transfer function, again Mason's gain formula can be applied to get the same transfer function. Then we have shifted to the time domain analysis. First, we have seen a first order system, how the output will look like for an impulse input, for a unit step input, and we have seen the waveform for unit step input. And then we have considered one RC circuit, and we have seen what will be the impulse response expression looks like. Then we have gone to second order system, and we have seen there are various nomenclature and how the damping of the system will affect the response of the system. And we have seen for unit step response, what are the settling time, rise time, peak time, percentage overshoot, and what are their expressions. And we have quickly solved one problem based on the same. So please remember this formula because it is crucial. Coming to the last topic of today's discussion, which is steady state error. In the steady state error, we have discussed about the calculation of steady state error using the final value theorem. So first, we need to get the expression for E of S. Once E of S is given, then we'll get this expression. So now R of S can be unit step, which is 1 by S, or unit ramp input, which is 1 by S square, or unit parabolic input, which is 1 by S cube. So depending upon this input, the output error, I mean steady state error can be 1 by 1 plus Kp, where Kp is position error constant, or 1 by Kb, where Kb is velocity error constant, or 1 by Ka, where K is acceleration error constant. So here we have asked whether the system is type 1 or type 0. It is type 1. And then we have calculated the error expression. And now we have given unit step input or unit ramp input. Depending upon that, we have calculated the steady state error. So this completes our week 3. Week 4, I will be taking on this Saturday 5 to 7, and week 5 I'll be taking on next Monday because I am attending one conference in the next month. I'll be away for 2 to 3 weeks. During that time, I'll not be able to take the problem solving sessions. So I'm planning to take them ahead so that the videos will be uploaded in the YouTube and you can always go through rather than postponing, because you need to have the video ready before the assignment submission. So I'm thinking to prepone my sessions. So this week Saturday also I'll take another extra session for week 4. If you have any questions, you can ask, else I'll end this session here.
Okay, sir. Thank you, sir.
Okay, thank you. You will get the notification from the NPTEL people. They will mail regarding my session on this Saturday, which will be from 4 to 6 if I'm not wrong. So they will share the link. Link will remains the same. Date and time they will share few days before. So please try to join on Saturday if you are available. Else the video will be uploaded to YouTube. You can go through it later. So if you have any doubts, you can ask. Else I'll end this session here.
Thank you, sir.
Okay, thank you. Thank you, everyone. I wish you all the best for your week 3 assignment. See you again on Saturday. Yeah, thank you, everyone. Niladri, thank you. Okay, then I'm ending this session.